Hi, this is Mark Roth, and this is Mathematics for Social Justice. Today's lesson is going to be the part one of constructing a bead necklace. We could construct it quickly, but I want to show teachers how to present it as a lesson that goes on for several days. So this particular necklace has 56 beads, 8 colors, 7 of each color, and every combination of 3 colors occurs just one time. So for example, I want to look for red, white, and blue. I'll eventually come to it. So this is the only time that red, white, and blue are next to each other. And I don't care which one's in the middle. The order doesn't matter. It's just the combination that I'm interested in. So when you have 8 objects, there's 56 combinations of 3. So we say 8 choose 3 is equal to 56. So once again, this necklace has 56 beads, 8 colors, 7 of each color, and every combination of 3 colors occurs just one time in the necklace. I was one of the people that discovered a method for constructing this. This is an example of a universal cycle. A different mathematician named Brad Jackson discovered another way to construct this necklace. But I'm going to be talking about my particular way. We're going to make a lesson out of this that could last several days with students. So first we're going to introduce the torus. Now the torus is basically the surface of a donut. So if we have a donut and we want to do things on the surface, it's kind of inconvenient because part of it is hard to see. We can't see the backside so well. So we're going to basically unwrap this torus and turn it into like a little square on the page. So we're going to take a cut. We're going to take a cut and open this up to make a cylinder. Then we're going to cut again and open it up to get like a sheet. So the way this works is if you're traveling here, you pop out the other end, and if you go like over here, you pop out the other side. So we can use this as our topological equivalent to this torus. So this is also the torus, but just the surface of it. Of course, well, actually, the torus is defined to be the surface of the donut only. So this is the torus. Now, we're going to try to triangulate this torus. And when you do a triangulation, triangles can only intersect so they intersect in one vertex. Or they can intersect where they share a complete edge of each. Or they cannot intersect at all. And we're going to try to find the minimum triangulation of the torus. And to do that, there's a shortcut. All we have to do is put 7 points on the torus and connect every point to every other point without crossing. So we're going to have this point be the same as this point because we're going to wrap over here. And we're still going to have these points still be the same point, because after you wrap this onto this, then they wrap down. So this point A is the same point. And then B is the same as this point here. And C is the same as this point here. And then D is the same as this point D here. E is the same as this point here. And then we have F and G. So altogether, we only have 7 points. And if we connect every point to every other point, we're going to automatically get the minimum triangulation of the torus. In other words, we'll be covering the torus with 14 triangles. And you can't triangulate the torus with less than 14 triangles. So to do that, you can have the students make a game of it. So you can have a student go to the board and A and B, A and C, A and D, A and E are already connected. So you can ask the student to connect A to F. So they can do it like this or like this. There's different ways for them to connect. Let's suppose they just do this. And then you say A to G, and they connect A to G. And then you say, well, B to C are already connected. So you say B to D. So maybe they try that. Then you say B to E. Maybe they try that. And then B to F. And B to G. So then you tell them to connect C to D, C to E, C to F, C to G, and then they're going to connect D to F and D to G. Well, there's a problem because maybe we should have done C to F like this. Now, a student wouldn't be allowed to do that. The student, if they have to erase, they would have to sit down and let some other student try. But we have C to F, we have C to G. Now we have D to F, D to G. Now we need E to F. It doesn't look like we can do E to F. So how could we fix this? Anyway, obviously this student sits down. Okay, so this is the completed triangulation. And let's double check that I connected every point to every other point. So we have A to B, A to C, A to D, A to E, A to F, and A to G, B to C, B to D, B to E, B to F, B to G, C to D, C to E, C to F, C to G, D to E, D to F, D to G, E to F, E to G, and F to G. So this should have given us 14 triangles. Next thing we're going to do is we're going to shade in every other one. So we'll shade in this one. And we'll leave this one blank, shade in this one. Leave this one blank, shade in this one. Leave this one blank and leave this one blank and shade in this one. Leave this blank and shade in this one. And shade in this one. Leave that blank, shade in this one. So now we're going to number each empty triangle. If we look at the three vertices around triangle 1, that's ABE. And for triangle 2, that's DEG. Triangle 3 is BCG. Triangle 4 is AFG. Triangle 5 is CEF. And triangle 6 is BDF. And triangle 7 is ACD. Now, this is a final plane. It consists of 7 lines 3 points on each line, and this will give me every pair one time only. So I'll have A and B in the same line, A and C, A and D, A and E, A and F, A and G, B and C, B and D, B and E, B and F, and B and G. I also have C and D, C and E, C and F, C and G, D and E, D and F, D and G, E and F, E and G, and F and G. So each one of the 21 possible combinations of 2 occur on a line in the 7 lines of the faunal plane. And so this is called the faunal plane, named after Gino Fano, an Italian mathematician. Remember, we're going to try to make a bead necklace with 56 bead, with every combination of 3 colors occurring once. Here we're going to use this to make a bead necklace that has only combinations of 2 colors. We can go like this: AD, and then we can do G, go to E, go to B, go to G, go to C, go to F, go to E, go to C, go to A, go to E, go to D, go to F, go to B, go to D, go to C, go to B again, go to A, go to F, go to G, and go to A. So when I go to A, I'm actually going back to this original A. So I can take this A and erase it, and take this G and D and move them here. So now I should have every pair of letters next to each other one time only. The order doesn't matter. I have A next to B, A next to C, A next to D, A next to E, A next to F, A next to G, B next to C, B next to D, B next to E, B next to F, B next to G, C next to D, C next to E, C next to F, C next to G, D next to E, D next to F, D next to G, E next to F, E next to G, and F next to G. So I have every combination of 2 letters next to each other one time in the necklace. And I did that using an Euler tour. So to create this necklace, I did something similar. But what I did is instead of having one letter at each vertex, I had two letters at each vertex. So if I had A and B here, I might have B and C here. And then I might have C and D here, D and E here. So when I do the first length, I'm actually doing A, B, C. And that's a triple. Okay, that's a combination of three letters. Then when I come to here, I add the new letter, which is D. When I come to here, I add the new letter, which is E. But I'm looking at this combination of letters, A, B, and C, B, C, and D, C, D, and E. So what I wanted to do is instead of create something where I don't have one letter at each corner, but I have, or each point, I have two letters at each corner. So suppose I wanted to make a necklace with 4 colors. So suppose I'm using 0, 1, 2, 3 as my colors. I tried this, 0, 1, 2, 3. And then here I could go from 0, 1 to 1, 2. And here I could go from 2, 3 to, so if I go 0, 1, 2, 3, here I want to go 0, 3. So when I make my first edge move, I'm going from 0, 1, and the new number is 2. So I have 0, 1, and then I have 2. When I come down here, I come to 3. And when I come to here, I come to the 0 again. And when I come to here, I come to this 1 again. So it's like a snake eating its own tail. When I do the last 2 rows, I'm repeating numbers that were already in my loop. So the next question I wanted to know is, what if you had 2 of these quadruples? Suppose you had 0, 1, 2, 3, and 2, 3, 4, 5. Now, I call this a quadruple. This quadruple has 4 triples. If I don't use the 3, it's 0, 1, 2. If I don't use the 2, it's 0, 1, 3. If I don't use the 1, it's 0, 2, 3. If I don't use the 0, it's 1, 2, 3. Here, if I don't use the 5, it's 2, 3, 4. If I don't use the 4, it's 2, 3, 5. If I don't use the 3, it's 2, 4, 5. If I don't use the 2, it's 3, 4, 5. So I want to see if I can make a necklace that uses all 8 of these triples. So what I did is I hooked them like this. I had 0, 1, 2, 3. Then I can go 0, 1, 2, 3. And here I have 2, 3, 4, 5. So 2, 3, 4, 5. Then I can go 2, 3, 4, 5. So notice these two numbers agree. This pair and this pair agree. They're the same where the attachment is. So I can start here, and I can start with 0, 1, 3. I come down to here, and my new number is 2. Now, I don't want to go here, because then I'd finish my loop early. So I want to go either to the right or down. It turns out it matters. You can't go both ways and finish your little necklace. You have to go to what I call the new number. So the new number here is 2, because if you look backwards, if you look in your rear view mirror, you already had a 3. So you have to go to the new number 2, which means you don't go to the right, you have to go down towards the 2. And now the new number is 4. And then you come to 5, and then to 3, and then to 2. And then when you come to 0, you already have it. And when you come to 1, you already have it. So the way to make the necklace is I need to come up with 14 of these quadruples. Because 14 of these quadruples will give me 4 times 14 triples, which is 56 triples. Now 8 choose 3 is 56. If you're choosing 3 things from 8, and you're not caring about order, you're only caring about combinations without worrying about the order, there's 56 ways to choose 3 things from 8. And we can calculate that on Pascal's triangle, or we can just do it with the multiplication principle. So when you choose 8 things at first, there's 8 choices you can make, and then there's 7 remaining, and then there's 6 remaining after that. But when you make this many choices, the order counts, and we don't care about the order when we do combinations. So we have to divide by the number of rearrangements. So when you have 3 things, there's 6 ways to rearrange them. So we want to count this as 1 combination, not as 6 combinations. So we have to divide by 6. And we can write it like this. 3 times 2 times 1. There's 3 things that could have been first here, 2 things that could have been second, and 1 remaining thing after that. So it turns out this 6 and this 6 cancel, and we do get 56. So there's 56 combinations. Now, what I'm trying to find then is 14 quadruples. And every quadruple has to give me 4 triples, and I end up with 56 triples with no repeats. So suppose I started with 0, 1, 2, 5. And I have 8 colors, so I'm going to be using the numbers 0 through 7 to represent the 8 colors. And suppose my next quadruple is 0, 1, 3, 6. And my next quadruple is 0, 2, 3, 7. So actually this will give me one way to finish. We're trying to build a Steiner quadruple system, which also is a BIBD, which stands for Balanced Incomplete Block Design. You can look up the definition, the formal definition of BIBD, Balanced Incomplete Block Design. It comes from statistics. So you can think of like, okay, you're testing like different kinds of fertilizers or something in an agricultural experiment, and you want to, instead of, you have 8 different kinds of fertilizers, but you only want to look at 4 at a time. So we want to finish this BIBD, or the Steiner quadruple system, so that the 4 triples that you get from each quadruple never get repeated. So for example, again, 0, 1, 2, 5. If you don't use the 5, you get 0, 1, 2. If you don't use the 2, it's 0, 1, 5. If you don't use the 1, it's 0, 2, 5. If you don't use the 0, it's 1, 2, 5. So the idea is to come up with 14 quadruples where the triples never get repeated. So to do that, there's no reason why any number should show up any more often than any other number. So if we have 14 quadruples, 14 times 4 is 56. And there's 8 different kinds of numbers, or colored beads. So if you divide 8 into 56, you get 7. So every number should show up 7 times. Now if we do the numbers in order, we're doing what's called the greedy algorithm. Which is something that's important in computer science in particular. So we already did 0, 1, 2, 5, 0, 1, 3, 6. We need 0, 1, 4, 7. Okay, so one way to calculate that, if you can't do it in your head, is to write 0, 1, and all the bigger numbers up to 7. So we already had 0, 1 with 2 and 5, cross out 2 and 5. We had 0, 1 with 3 and 6, cross out 3 and 6. And what's left? 4 and 7. So there's the 4 and the 7. Now, we used 0, 1, 0, 1, 0, 1. Let's make sure we don't need 0, 1 again. I don't think we do, but let's make sure. So there's 8 different kinds of numbers. And if we choose 2 of them, we're doing 8 choose 2. So 8 choose 2 is 8 times 7 divided by 1 times 2, which is 56 divided by 2, which is 28. So there's 28 different kinds of doubles. 0, 1, we can call a double. And there's 28 different kinds. Now, how many doubles are there in the whole Steiner quadruple system when we're done? Well, each quadruple has 6 doubles. We have 0, 1, 0, 2, 0, 5, 1, 2, 1, 5, 2, 5. That's 6 doubles. 6 times 14 is 84. So we have 84 doubles when we're done, and 28 different kinds. That goes in 3 times. So we do want each double 3 times. So after we do 0, 2, 3, 7, we need one more 0, 2. So I already did 0, 2 with 5, 0, 2 with 3, 7. We need 4, 6. And now we got to count 0, 3s. We have 0, 3, 0, 3. We need one more 0, 3. So there's 0, 3, 0, 3. We need one more 0, 3. We already had 0, 3 with 6 and 0, 3 with 7. We need 0, 3 with 4 and 5. And now we got to count the 0, 4s. We've had 0, 4 once, 0, 4 twice, 0, 4 3 times. So we probably need 0, 5. We had 0, 5 here with nothing bigger, 0, 5 here with nothing bigger. So we need 0, 5, 6, 7. So now we need 7 ones. 1, 2, 3, we need 4 more. So we've already had 1, 2 once. We need 1, 2 twice more. So we have to look at to see if we've had 1, 2, 3 yet. We've had 1, 2, 5. We haven't had 1, 2, 3 yet. So let's get that out the way. Now to get the 4th number, this is complicated because we not only have to look at the previous 1, 2s, we have to look at the previous 1, 3s and the previous 2, 3s. So if we write 1, 2, 3, and the bigger number is up to 7, we already had 1, 2 with a 5. We cross out a 5. We've had 1, 3 with a 6. So we cross out a 6. And we had 2, 3 with a 7. We cross out a 7. So this has to be 4. And after we have 1, 2, 3, 4, and 1, 2, 5, we need 1, 2, 6, 7. So next, we can look at the previous 1, 3s. So we've had 1, 3 once, 1, 3 twice. We need 1, 3 a 3rd time. And we've already had 1, 3, 6 and 1, 3, 4. So we need 1, 3, 5, 7. Now we look at the previous 1, 4s. 1, 4, 1, 4. This 1, 4 had nothing bigger. This 1, 4 had a 7. So we need 5 and 6. So now we have to count the 2s. We had 1, 2, 3, 4, 5. We need 2 more. And we haven't had, now let's look at the previous 2, 3s. We've had 2, 3 once, 2, 3 twice. We need 2, 3 a 3rd time. This 2, 3 had a 7. This 2, 3 had a 4. We need 5 and 6. And now we count 2 4s. 2, 4 once, 2, 4 twice, we need 2, 4 a third time. This 2, 4 had a 6, so we need a 5 and a 7. So now we count threes. 1, 2, 3, 4, 5, and 6. We need a 7th 3. Now let's count the 3 4s. We've had 3 4 once, 3 4 twice. We need 3 4 a third time. This 3 4 had a 5, so we need 6 and 7. Could we have developed this easier? In particular, is there a geometrical way of getting these numbers? So right away, when I'm thinking of 8 different kinds of numbers, I'm thinking, what kind of geometry has 8 things? So I'm thinking the corners of a cube. So just for the heck of it, let's draw a cube. So let's put this 0, 1, 2, 5 on the face on one of the faces of the cube. And let's put 0, 1, 3, 6 on the face of a cube. So 0, 2, 3, 7. I could put 0, 2, 3, 7 on the left face of the cube. And let me see where I have 3, 6, and 7 together. Right here, 3, 6, and 7. So that should be 4. So let's look at the 6 faces of the cube. We have 0, 1, 2, 5 on top. On the back, we have 0, 1, 3, 6. On the right side, we have 1, 4, 5, 6. Okay. On the left, we have 0, 2, 3, 7. And the front is 2, 4, 5, 7. So 0, 1, 2, 5, this was the top. And 0, 1, 3, 6, that was the back. 0, 2, 3, 7, that was the left. 1, 4, 5, 6, that was the right. 2, 4, 5, 7, that was the front. So I got front and back, left and right, top, I need bottom. So the bottom is 3, 4, 6, 7. So I have all the faces of the cube. So what would 0, 1, 4, 7 be? 0, 1, 4, 7 would be like slicing through a cube of cheese from the top back to the front bottom. It's like a diagonal slice. So 0, 1, 4, 7 is a diagonal slice. So I could also slice like that, 1, 5, 3, 7. 0, 1, 5, 3, 7, or 1, 3, 5, 7. Yeah. So I'm going to write slice. Slice. Now I can slice like that, 0, 3, 0, 3, 4, 5. That's also a slice. And I could slice like this, 1, 2, 6, 7. That's a slice. And 0, 2, 4, 6 is a slice. How many slices now? I got slice, 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 slice. I think there's one more slice if I can find it. Slicing down like this. 2, 3, 5, 6. Okay, so I'm left with 2 more. Okay, there's 6 slices and 6 faces. We have 2 more things. So 0, 5, 6, 7. So 0, 5, 6, 7 is like a crisscross. I'm going like this on the top and like this on the bottom. Actually, these would be the 4 vertices of an inscribed tetrahedron, where each edge of the tetrahedron is a diagonal through a square of the cube. But you can just think of it as a crisscross. So I got boom, 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 boom. And the other way to do boom, 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 boom would be like X, 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 X. 1, 2, 3, 4. So this would, we'll call that a crisscross. And this is also a crisscross. So it turns out that this Steiner quadruple system, this balanced incomplete block design, can be made determined very quickly by looking at the 6 faces of the cube, the 6 diagonal slices through the cube, and the 2 ways to crisscross. And we get all 14 quadruples. And then, in order to finish the necklace, all I would have to do is hook up 14 squares like this. So I could, if I had like 1, 2, 3, 4, and I went 1, 2, 3, 4, here I'd have to have it, I could have, say, 3, 4, 5, 6, 3, 4, 5, 6. So all I'd have to do is make a square for each of these quadruples, hook them together so that the corners agree, and then go around the outside, and I would be done with my necklace. The only problem is there's still more shortcuts, and we're trying to do this as efficiently as possible. So one thing we didn't notice yet was let's go back to this part here. There's something to notice if we look at like this much. If we look at these, there's something to notice. If we look at these two, we have all eight numbers. If we look at these two, we have all 8 numbers. If we look at these two, we have all 8 numbers. Well, that makes sense because that's sort of what's going on with a cube. When you have these 4 numbers, you have the other 4 numbers as 2 kind of parallel sides of the cube. So then also, if you look at just the zeros, if you look at the numbers that are remaining, if you just look at 1, 2, 5, 1, 3, 6, 1, 4, 7, 2, 3, 7, 2, 4, 6, and 3, 4, 5, and 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. We get one of these final planes. So if we take the final plane and add a 0 in front, and then give the complements. So in other words, if there was a very quick way to come up with the final plane, we could do our necklace really quickly. And actually there is a quick way to do the final plane. There's a famous picture. You start with a triangle and you draw its medians. And then you draw kind of its inscribed circle. So, for example, you could put 0 here, 1 here, 2 here, 3 here, 4 here, 5 here. So we get 7 numbers. Okay, 0 through 6. And we get a final plane. So each edge gives us a triple. So we have 0, 1, 2, 0, 3, 6, 0, 3, 4. No, wait. I'm sorry, 0, 1, 2. That was 1, 3, 6, not 0, 3, 6. And 0, 3, 4. And then we do the medians. So 0, 5, 6, 2, 3, 5, and 1, 4, 5. Now it doesn't look like a line, but this circle is actually a line in this finite geometry. So the last triple is 2, 4, 6. So this is a final plane. So if I wanted to make the necklace, all I would have to do is this. Add another color. And then do the complements. So 0, 1, 2, 7, I didn't use 3, 4, 5, or 6. And 1, 3, 6, 7, I didn't use 2, 4. I didn't use 0, 2, 4, or 5. And 0, 3, 4, 7, I didn't use 1, 2, 5, or 6. So basically, I can make the necklace really quickly. All I have to do is draw this, put numbers down, draw the final plane, draw the complements, and I have 14 quadruples. Then I hook the quadruples together. So, for example, this is 1, 2, 3, 4. 1, 2, 3, 4. This is 3, 4, 5, 6. 3, 4, 5, and 6. And then I just have to move around. But I have to be careful because when I come to here, I have to go to the new number. When I come to here, the new number is 3. I do 1, 2, 4, and then the new number is 3. So I have to be careful to go to the new number 3 and not to the old number 4. Well, that might slow me down, and I might make a careless mistake and go to the new number. So another improvement would be, I just want to go around the outside. I don't want to bother about worrying about each intersection if I go down or I go to the right. So what I want to do instead is do this. Okay, so here's a quick way to make the necklace. Instead of putting 2 numbers at each corner, do this. Suppose I'm using like colors now. So I can go blue, brown, red, and blue. And when I connect that to another one, so this is going to be brown. No, wait a minute. Blue, brown, red, and it's like green. Okay? So when I do this one, this green and this green have to crisscross. And this red have to crisscross. So it's a crisscross situation. And then this can be any 2 other colors, yellow and purple, say. So then to make the necklace, I just hook them so that the colors crisscross. They agree, but they crisscross. And then I get the necklace real easy. I don't have to worry about going to the number. So I just go brown, red, green, purple, yellow, red, green, and blue. And I make my necklace. So instead, I have to have 14 of these hooked together, and then I just go around the outside, just make sure that the colors crisscross. So let me do this again real quickly. I'll see how fast I can go. So I draw this diagram. So triangle, medians, inscribed circle. So I'm not going to use blue. I'll be using brown, green, orange, purple, red, yellow, and white. So those will be my colors. So then I'll do the outside edges. So I'm going to have brown, green, and orange. And then I'm going to use the other color I didn't use. So that's blue. So then I'm going to do green, purple, and red. And again, add the blue. And I'm going to do brown, purple, and yellow, and add the blue. And I'm going to do the medians. So it's going to be brown, red, and white, and add the blue. Okay, so then it's going to be purple, orange, purple, and white, add the blue. So I think I need one more median, green, white, and yellow, add the blue. Now I'm going to do the circle, or the inscribed circle. So it's going to be orange, red, and white, orange, red, and yellow, add the blue. Now I do the complements. So the complement of blue, brown, green, orange would be purple, red, white, and yellow. And when I do the complement of this, it's going to be brown, orange, white, and yellow. When I do the complement of this, it's going to be green, orange, red, and white. Well, you can see what's happening. When I'm done with the complements, I'll have 14 of these quadruples. And then, so when I have a square, for example, for this particular thing, I can write blue, brown, green, and orange. When I connect this to it, so I need another one that has green and orange. This one has green and orange. So I can write, the oranges have to crisscross, the greens have to crisscross, and I can put either red, white, or white, red, doesn't matter. So then to make the necklace, I just go around, brown, orange, green, red. Of course, I'm going to have 14 of these squares hooked together. That's all you have to do. You can do it fast and you'll complete your necklace. If you do this in school, you can break this into several days. So this is what the completed bead necklace looks like. I think they're about 14 millimeters. I bought the beads at Annabelle's. In Los Angeles. I string the beads on ball chain. Which you can buy on Amazon, and also the connectors you can buy on Amazon. And you can also buy plastic sealed bags at Annabelle's to store the beads in.